What if the very fabric of reality began with a single, mysterious spark? A moment so profound that it set the stage for everything we know today. Imagine a time when the universe was nothing more than a swirling sea of potential, waiting for the first flicker of order to emerge. This is the story of quantum coherence, the hidden force that may hold the key to understanding the universe's earliest moments. From the Big Bang to the multiverse, from black holes to cosmic strings, we're about to dive into 30 groundbreaking theories that explore how the first quantum coherence shaped the cosmos as we know it. Each theory is a piece of the puzzle, offering a unique perspective on the origins of existence. So, are you ready to unravel the mysteries of the universe's first quantum coherence? Stay with us because by the end of this journey, you'll see the cosmos in a whole new light. Let's begin. Now, let's step into the very beginning, the moment when everything we know came into existence. The Big Bang wasn't just an explosion, it was the birth of spacetime itself, a chaotic yet incredibly precise event. During this explosive beginning, the universe was a hot, dense soup of energy and particles, constantly shifting and changing. But within this chaos, something extraordinary happened: quantum fluctuations. These tiny, random variations in energy and matter were like ripples on the surface of a vast cosmic ocean. As the universe expanded rapidly during a phase called inflation, these quantum fluctuations were stretched and amplified, creating the seeds for the first quantum coherence. Think of it like this: if the early universe was a blank canvas, these fluctuations were the first brushstrokes, setting the stage for the intricate patterns of galaxies, stars, and planets we see today. Inflation didn't just stretch space, it also smoothed out these fluctuations, allowing them to become the building blocks of structure in the cosmos. But here's where it gets even more fascinating. These fluctuations weren't just random noise, they carried the potential for order. As the universe cooled and expanded, the quantum coherence that emerged from these fluctuations began to shape the fabric of reality itself. It's as if the universe was tuning itself, finding the right balance between chaos and order. This delicate interplay between quantum fluctuations and inflation is what gave rise to the first coherent structures, laying the foundation for everything that followed. So, when we look at the night sky, we're not just seeing stars and galaxies, we're witnessing the echoes of those first quantum fluctuations, the fingerprints of the universe's earliest moments. And that's just the beginning. Next, we'll explore how the holographic principle suggests that the entire universe might be encoded on a two-dimensional surface, offering a completely new perspective on quantum coherence. Stay with us, this journey is only getting started. Now, let's shift our perspective and dive into a theory that turns our understanding of the universe inside out, literally. The holographic principle suggests something mind-bending. The entire universe, with all its complexity and three-dimensional grandeur, might actually be encoded on a two-dimensional surface. Imagine your entire reality, every star, every galaxy, even you, being projected from a flat cosmic screen. It's like the universe is a hologram where all the information needed to describe it is stored on its boundary, not within its volume. This idea emerged from the study of black holes, where physicists discovered that the information about everything falling into a black hole isn't lost but is instead encoded on its event horizon, the two-dimensional surface surrounding it. Extending this concept to the entire universe, the holographic principle proposes that the fabric of reality itself could be a projection from a lower dimensional surface. But what does this mean for quantum coherence in the early universe? If the universe's quantum coherence is encoded on a two-dimensional surface, it could explain how such a vast and complex system emerged from something seemingly simpler. In the early moments of the cosmos, this encoding might have allowed quantum information to be stored and processed in a way that enabled the first coherent structures to form. It's as if the universe was running a cosmic algorithm, with the two-dimensional surface acting as the code and the three-dimensional reality as the output. This principle also challenges our understanding of space and time. If the universe is a hologram, then space as we know it might be an illusion, a projection of deeper, more fundamental processes. This could mean that the quantum coherence we observe today is just the tip of the iceberg, hinting at a deeper layer of reality where the true nature of the universe is written in two dimensions. The implications for cosmology are profound. If the holographic principle is correct, it could revolutionize how we think about the Big Bang, inflation, and the very nature of spacetime. It suggests that the universe's earliest moments might have been governed by a kind of quantum code, written on a cosmic canvas that we're only beginning to decipher. As we continue this journey, we'll explore how loop quantum gravity offers another fascinating perspective on the universe's first quantum coherence, suggesting that spacetime itself might be made of tiny, discrete loops. The mysteries of the cosmos are far from solved, but each theory brings us closer to understanding the grand tapestry of existence. Stay curious, there's so much more to uncover. Now, let's take a step into a theory that reimagines the very fabric of spacetime itself. Loop quantum gravity proposes a radical idea. Instead of being smooth and continuous, spacetime might be made up of tiny, discrete loops, like a cosmic tapestry woven from the smallest threads imaginable. Picture the universe not as a seamless expanse, but as a network of interconnected loops, each one a fundamental building block of reality. This theory challenges the traditional view of spacetime and offers a fresh perspective on how the universe's first quantum coherence might have emerged. At the heart of loop quantum gravity is the idea that spacetime is quantized, meaning it's divided into the smallest possible units. These units, or loops, are so tiny that they're far beyond our current ability to observe directly. But their existence could explain how the universe transitioned from a chaotic quantum state to the coherent structures we see today. In the early moments of the cosmos, these loops might have acted like the pixels of a cosmic screen, providing a framework for quantum coherence to take hold. It's as if the universe was knitting itself together, one loop at a time, to create the fabric of spacetime we experience. One of the most intriguing aspects of loop quantum gravity is its connection to the Big Bang singularity. Traditional physics breaks down when we try to describe the singularity, a point of infinite density and temperature where the laws of physics as we know them cease to apply. But loop quantum gravity suggests that the singularity might not have been a true infinity. Instead, the discrete nature of spacetime could have prevented the universe from collapsing into an infinitely dense point. This means the Big Bang might not have been the beginning of everything, but rather a transition from a previous state of the universe. In this scenario, quantum coherence could have played a key role in stabilizing the universe as it emerged from this transition. The implications of this theory are profound. If spacetime is made of loops, it could mean that the universe's earliest moments were governed by a kind of quantum geometry, where the rules of classical physics didn't yet apply. This quantum geometry might have allowed for the first coherent structures to form, setting the stage for the universe as we know it. It's a vision of the cosmos that's both elegant and deeply mysterious, offering a new way to think about the origins of reality. As we move forward, we'll explore how string theory and the concept of branes add yet another layer to our understanding of the universe's first quantum coherence. Each theory weaves a different thread into the cosmic tapestry, bringing us closer to unraveling the mysteries of existence. Stay with us, there's so much more to discover. Now, let's shift our focus to a theory that takes us into the realm of higher dimensions and vibrating strings. String theory introduces a fascinating idea. The universe might not be built from point-like particles, but from tiny, one-dimensional strings vibrating at different frequencies. These strings are thought to be the fundamental building blocks of everything, from the smallest particles to the vast structures we see in the cosmos. But string theory doesn't stop there. It also introduces the concept of branes, multidimensional surfaces that could hold the key to understanding the universe's first quantum coherence. Imagine branes as vast, flexible sheets existing in higher dimensional space. According to string theory, our entire universe could be a three-dimensional brane floating in a higher dimensional realm. The collision of two such branes could have been the spark that ignited the Big Bang, setting the stage for the birth of our universe. This collision wouldn't just have created matter and energy, it might also have triggered the first instances of quantum coherence on a cosmic scale. Picture it like ripples spreading across a pond after a stone is thrown, but on a scale so immense that it shaped the very fabric of reality. One of the most intriguing aspects of this theory is how it connects quantum coherence to the geometry of higher dimensions. When branes collide, the energy released could have created a burst of quantum activity, causing particles to synchronize their states across vast distances. This synchronization, or coherence, might have been the foundation for the orderly structures we observe in the universe today. It's as if the collision of branes acted like a cosmic conductor, orchestrating the first notes of the universe's symphony. String theory also offers a unique perspective on the nature of spacetime. In this framework, spacetime isn't just a passive backdrop, it's an active participant, shaped by the interactions of strings and branes. This dynamic interplay could have allowed quantum coherence to emerge naturally, as the universe settled into its new state after the collision. The idea that our universe's coherence might be rooted in the vibrations of strings and the geometry of branes is both mind-bending and deeply compelling. As we continue our journey, we'll explore how the multiverse hypothesis adds yet another layer to this cosmic puzzle. Each theory we encounter brings us closer to understanding the profound mysteries of the universe's earliest moments. Stay with us, there's so much more to uncover. Now, let's venture into a theory that stretches the boundaries of our imagination, the multiverse hypothesis. This idea suggests that our universe might not be alone. Instead, it could be just one of countless universes, each with its own unique set of physical laws and constants. Picture an infinite cosmic tapestry where every thread represents a different universe, some similar to ours, others wildly different. In this vast multiverse, the emergence of quantum coherence in our universe might not be a random event but a consequence of the broader cosmic landscape. The multiverse hypothesis raises a fascinating question. Could the quantum coherence we observe in our universe be the result of interactions between multiple universes? Some theories propose that these universes aren't entirely isolated. Instead, they might interact or overlap in ways that influence each other's development. Imagine two bubbles floating close together in a vast ocean. When they touch, they exchange energy and information. Similarly, our universe's quantum coherence might have been shaped by subtle interactions with neighboring universes, creating the conditions for order and structure to emerge. One of the most compelling aspects of this theory is how it explains the fine-tuning of our universe. Why do the fundamental constants of nature, like the speed of light or the strength of gravity, have the precise values they do? In a multiverse, these constants could vary from one universe to another. Our universe's specific combination of constants might be the reason quantum coherence was able to take hold, allowing for the formation of galaxies, stars, and ultimately, life. It's as if our universe won a cosmic lottery with the right conditions to foster coherence and complexity. But the multiverse hypothesis doesn't stop there. It also opens the door to the possibility of universes with entirely different forms of quantum coherence, or none at all. In some universes, the laws of physics might prevent coherence from ever forming, leading to chaotic, disordered realities. In others, coherence might manifest in ways we can't even imagine, giving rise to entirely new forms of matter and energy. This diversity of possibilities challenges us to rethink what we know about the nature of reality itself. As we explore this theory, it's worth considering how the multiverse might influence our understanding of the universe's earliest moments. Could the birth of our universe have been part of a larger cosmic event, involving multiple universes coming into existence simultaneously? And if so, how did these interactions shape the first instances of quantum coherence? These questions push the boundaries of our knowledge, inviting us to consider a reality far more complex and interconnected than we ever imagined. Next, we'll dive into the role of quantum entanglement at the dawn of time, exploring how particles linked across vast distances might have played a crucial role in the universe's first coherence. The journey continues and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's shift our focus to a phenomenon that seems almost magical: quantum entanglement. This strange and fascinating feature of quantum mechanics suggests that particles can become deeply connected, no matter how far apart they are. Imagine two particles separated by billions of light years, yet still influencing each other instantaneously. It's as if they share a secret language, communicating faster than the speed of light. But could this bizarre connection have played a role in the universe's first moments, helping to establish the earliest quantum coherence? Quantum entanglement is often described as a kind of cosmic glue, binding particles together in ways that defy our everyday understanding of space and time. At the dawn of the universe, when everything was incredibly small and dense, particles would have been packed tightly together, creating the perfect conditions for entanglement to occur. As the universe expanded, these entangled particles might have carried their connections with them, spreading coherence across vast distances. This could explain how the early universe transitioned from a chaotic, disordered state to one with structure and order. One of the most intriguing ideas is that entanglement didn't just link individual particles, it might have connected entire regions of the universe. Picture a web of entangled particles stretching across the cosmos, creating a network of coherence that allowed the first galaxies and stars to form. This interconnectedness could have been the foundation for the large-scale structure we see today, from galaxy clusters to the cosmic web itself. In this view, entanglement wasn't just a side effect of the early universe, it was a driving force shaping the very fabric of reality. But how exactly did entanglement lead to coherence? One possibility is that entangled particles acted like tiny messengers, carrying information about their quantum states across the universe. This exchange of information could have synchronized the behavior of particles, creating a kind of cosmic harmony. Over time, this synchronization might have grown, allowing larger and more complex structures to emerge. It's like a symphony where each particle plays its part, guided by the invisible threads of entanglement. This theory also raises profound questions about the nature of time and causality. If entangled particles can influence each other instantaneously, does that mean the past, present, and future are more interconnected than we realize? Could the universe's first coherence have been a result of events that happened not just in the early moments of the Big Bang, but across the entire timeline of the cosmos? These questions challenge our understanding of cause and effect, suggesting that the universe's history might be far more complex than we ever imagined. As we explore the role of quantum entanglement in the universe's first coherence, we're reminded of just how interconnected everything truly is. From the smallest particles to the largest structures, the cosmos seems to be woven together by invisible threads, binding the past, present, and future into a single, coherent whole. Next, we'll turn our attention to the mysterious force driving the universe's expansion, dark energy, and how it might have influenced the formation of quantum coherence. The journey continues and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's venture into the enigmatic realm of dark energy, a force that continues to baffle scientists and shape the fate of our universe. While quantum entanglement weaves the fabric of reality at the smallest scales, dark energy operates on the grandest stage, driving the accelerated expansion of the cosmos. But could this mysterious force have also played a role in the universe's first quantum coherence? Let's explore this intriguing possibility. Dark energy, which makes up about 68% of the universe, is often described as the anti-gravity force pushing galaxies apart at an ever-increasing rate. Its presence was first inferred from observations of distant supernova, revealing that the universe's expansion isn't slowing down, it's speeding up. But what does this have to do with quantum coherence? To understand this, we need to look back to the universe's earliest moments, when dark energy might have been just as influential as it is today. In the early universe, dark energy could have acted as a kind of cosmic stabilizer, smoothing out fluctuations and creating the conditions necessary for coherence to emerge. Imagine a turbulent sea of particles, each jostling for position in a chaotic dance. Dark energy, with its repulsive force, might have provided a counterbalance, allowing particles to align and synchronize their quantum states. This alignment could have been the first step toward the organized structures we see today, from galaxies to galaxy clusters. One fascinating idea is that dark energy didn't just influence the expansion of space, it might have also shaped the quantum landscape itself. As the universe expanded, dark energy could have stretched the fabric of spacetime, creating regions where quantum coherence was more likely to form. These regions might have acted as seeds, giving rise to the first coherent structures in the cosmos. Over time, these seeds could have grown, evolving into the complex web of galaxies and cosmic filaments we observe today. But dark energy's role doesn't stop there. Some theories suggest that it might have interacted directly with quantum fields, amplifying their coherence and helping to stabilize the early universe. This interaction could have been a delicate balancing act, with dark energy providing just the right amount of push to keep the universe from collapsing back into chaos. In this view, dark energy isn't just a passive observer. It's an active participant in the story of cosmic coherence. Of course, this raises new questions. If dark energy played such a crucial role in the early universe, why does it dominate so much of the cosmos today? And how did it interact with other forces like gravity and quantum entanglement to shape the universe's evolution? These questions remind us that dark energy is still one of the greatest mysteries in modern physics, and its connection to quantum coherence is just one piece of a much larger puzzle. As we ponder the role of dark energy in the universe's first coherence, we're reminded of the delicate interplay between forces that shape our cosmos. From the smallest quantum fluctuations to the vast expanse of space, every element seems to play a part in the grand cosmic symphony. Next, we'll turn our attention to another fascinating phenomenon, the quantum Zeno effect, and how it might have helped stabilize the universe's earliest moments. The journey continues and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's shift our focus to a phenomenon that sounds almost like science fiction, but is deeply rooted in the principles of quantum mechanics, the quantum Zeno effect. Named after the ancient Greek philosopher Zeno of Elea, who proposed paradoxes about motion and change, this effect suggests that simply observing a quantum system can freeze its state, preventing it from evolving. But how could this peculiar behavior have influenced the universe's first quantum coherence? Let's dive in. At its core, the quantum Zeno effect hinges on the idea that frequent observation of a quantum system can halt its natural progression. Imagine flipping a coin repeatedly. If you check it after every flip, it's more likely to stay in the same state rather than transitioning between heads and tails. In the quantum world, this means that constant measurement can keep a particle locked in a specific quantum state, effectively stabilizing it. Now, apply this concept to the early universe, a time when quantum fluctuations were rampant and coherence was just beginning to emerge. In those chaotic first moments, the universe was a seething cauldron of particles and energy, with quantum states flickering in and out of existence. The quantum Zeno effect could have acted as a kind of cosmic pause button, allowing certain quantum states to stabilize long enough for coherence to take hold. Think of it as a sculptor chiseling away at a block of marble. Each observation, like each strike of the chisel, refines the form, bringing order out of chaos. In this case, the sculptor might have been the universe itself, constantly interacting with its own quantum states. One intriguing possibility is that the quantum Zeno effect didn't just stabilize individual particles, it could have synchronized entire regions of the early universe. By repeatedly observing these regions, whether through natural processes or interactions with other quantum fields, the universe might have created pockets of coherence that eventually grew into the structures we see today. This synchronization could have been the first step toward the organized cosmos we inhabit, from the tiniest particles to the largest galaxies. But here's where it gets even more fascinating. Some theories suggest that the quantum Zeno effect might have worked hand in hand with other forces, like dark energy or quantum entanglement, to shape the early universe. For instance, dark energy's repulsive force could have stretched spacetime, creating conditions where the Zeno effect was more likely to occur. Meanwhile, quantum entanglement might have linked particles across vast distances, allowing the Zeno effect to stabilize coherence on a cosmic scale. Together, these forces could have woven the intricate tapestry of the universe we know today. Of course, this raises questions about what observation means in the context of the early universe. Was it a natural process like the interaction of quantum fields, or something more profound? And how did the quantum Zeno effect transition from stabilizing individual particles to shaping the entire cosmos? These questions remind us that the quantum Zeno effect, while powerful, is just one piece of the puzzle in understanding the universe's first coherence. As we explore the quantum Zeno effect's role in the early universe, we're reminded of the delicate balance between observation and evolution, between chaos and order. It's a reminder that even the smallest actions, like the act of observation, can have profound consequences on the grandest scales. Next, we'll turn our attention to another captivating idea: the emergence of time itself, and how it might have been intertwined with the universe's first quantum coherence. The journey continues, and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's step into a realm where time itself becomes a puzzle, a concept so fundamental yet so mysterious. What if time, as we know it, didn't always exist? What if it emerged from the very fabric of quantum coherence in the early universe? This is the heart of Theory 9, a mind-bending idea that challenges our understanding of causality and the nature of reality. At the core of this theory is the notion that time might not be a fixed, unchanging backdrop, but rather a dynamic feature that arose from the quantum processes of the early universe. Imagine the universe in its infancy, a swirling, chaotic sea of quantum fluctuations. In this primordial soup, particles and energy were constantly interacting, flickering in and out of existence. It's within this chaos that some scientists propose time began to take shape, emerging as a byproduct of quantum coherence. But how does this work? One way to think about it is through the lens of quantum entanglement. When particles become entangled, their properties are linked, no matter how far apart they are. This interconnectedness could have created a kind of quantum clock, where the synchronization of entangled particles gave rise to the first ticks of time. In other words, time might have started as a way to keep track of these quantum relationships, evolving into the linear flow we experience today. This idea turns our traditional understanding of causality on its head. In classical physics, cause and effect follow a clear, linear timeline. Events happen in a sequence, and time marches forward. But if time itself emerged from quantum coherence, the early universe might have operated under different rules. Cause and effect could have been intertwined, with events influencing each other in ways that defy our everyday experience. It's as if the universe was playing by a different set of rules before time as we know it took hold. Some theories even suggest that the emergence of time was tied to the universe's transition from a quantum state to a classical one. As quantum coherence stabilized and the universe cooled, the chaotic quantum fluctuations began to settle into more predictable patterns. This transition could have marked the birth of time, as the universe shifted from a state of pure potential to one where events could unfold in a sequence. It's a bit like watching a blurry image come into focus. Time sharpens the picture, giving structure to the cosmos. But here's where it gets even more intriguing. If time emerged from quantum coherence, what does that mean for the very beginning of the universe? Could there have been a pre-time era where the concept of before and after didn't exist? And if so, how did the universe transition from this timeless state to one where time flows? These questions push the boundaries of our understanding, inviting us to rethink not just the origins of time but the nature of reality itself. As we explore this theory, we're reminded that time is more than just a measure of change. It's a fundamental aspect of the universe's structure. The idea that time emerged from quantum coherence challenges us to see the cosmos in a new light, where even the most basic concepts are open to reinterpretation. Next, we'll delve into another fascinating piece of the puzzle: the role of black holes in shaping the universe's first quantum coherence. The journey continues and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's turn our attention to one of the most enigmatic objects in the cosmos: black holes. These mysterious entities, often thought of as cosmic vacuum cleaners, might have played a surprising role in the universe's first quantum coherence. This is the heart of Theory 10, which suggests that primordial black holes could have acted as catalysts, creating pockets of order in the otherwise chaotic early universe. To understand this idea, we need to rewind to the universe's infancy, a time when everything was incredibly dense and hot. In this turbulent environment, tiny fluctuations in density could have led to the formation of primordial black holes that formed not from collapsing stars, but directly from the intense pressures of the early universe. These black holes, though small, would have been incredibly powerful, exerting a strong gravitational influence on their surroundings. Here's where things get fascinating. Some scientists propose that these primordial black holes could have served as focal points for quantum coherence. Imagine a chaotic sea of particles and energy, constantly interacting and fluctuating. In such an environment, the gravitational pull of a black hole could have created a localized region of stability where quantum states could align and synchronize. In other words, black holes might have acted like cosmic anchors, bringing order to the chaos and allowing quantum coherence to take hold. But how exactly does this work? One possibility is that the intense gravitational fields of black holes could have influenced the behavior of nearby particles, causing them to become entangled and synchronized. This entanglement could have spread outward, creating a ripple effect of coherence that extended beyond the immediate vicinity of the black hole. Over time, these pockets of coherence could have grown, eventually contributing to the larger-scale structure of the universe. This theory also raises intriguing questions about the relationship between black holes and the fabric of spacetime itself. If black holes played a role in establishing quantum coherence, they might have also influenced the emergence of spacetime as we know it. Some researchers even suggest that the information swallowed by black holes could be encoded in the quantum states of the surrounding particles, creating a kind of cosmic memory that shaped the early universe. Of course, this is still a speculative idea, and much remains to be explored. But if primordial black holes did indeed act as catalysts for quantum coherence, it would mean that these mysterious objects were not just destructive forces but also creative ones, helping to shape the universe in its earliest moments. As we continue to unravel the mysteries of black holes, we may find that they hold the key to understanding not just the origins of quantum coherence, but the very nature of reality itself. With this theory in mind, we're reminded that the universe is full of surprises, and even the most unlikely players can have a profound impact on its story. Next, we'll dive into another fascinating concept, the quantum foam hypothesis, which explores the idea that the universe's first coherence might have emerged from a seething sea of virtual particles. The journey through the cosmos continues, and the mysteries only grow deeper. Stay with us, there's so much more to uncover. Now, let's shift our focus to a concept that takes us even deeper into the quantum realm, the quantum foam hypothesis. This theory paints a picture of the early universe as a bubbling, chaotic sea of virtual particles, constantly popping in and out of existence. It's within this turbulent environment that the first hints of quantum coherence might have emerged, setting the stage for the universe as we know it. To grasp this idea, we need to think about the very fabric of spacetime at the smallest scales. According to quantum mechanics, even empty space isn't truly empty. Instead, it's a dynamic, ever-changing landscape where particles and antiparticles spontaneously appear and vanish in a fraction of a second. This phenomenon is often referred to as quantum foam, and it's thought to be the foundation of reality at the tiniest levels. So, how does this chaotic foam relate to quantum coherence? Imagine the early universe as a boiling pot of water, with bubbles forming and bursting at an incredible rate. In this analogy, the bubbles represent virtual particles, and the foam itself is the underlying structure of spacetime. Now, picture a moment when some of these bubbles begin to align, creating a pattern or rhythm amidst the chaos. This alignment could have been the first step toward quantum coherence, where particles start to synchronize and work together rather than acting randomly. One possibility is that fluctuations in the quantum foam created regions where particles became entangled, linking their quantum states across vast distances. This entanglement could have acted as a kind of glue, binding particles together and allowing them to share information. Over time, these entangled regions might have grown, forming the seeds of larger structures in the universe. In this way, the quantum foam could have served as the substrate for the first coherent quantum states, providing the raw material for the universe's earliest moments of order. But the quantum foam hypothesis doesn't just stop at coherence, it also challenges our understanding of spacetime itself. If spacetime is fundamentally frothy and dynamic at the smallest scales, it raises questions about how smooth, continuous spacetime emerges on larger scales. Some scientists suggest that the transition from quantum foam to classical spacetime might have been a crucial step in the universe's evolution, paving the way for the formation of stars, galaxies, and ultimately life. Of course, this is still a highly speculative idea, and much of it remains in the realm of theoretical physics. Yet, it offers a fascinating perspective on how the universe's first moments of order might have arisen from chaos. The quantum foam hypothesis reminds us that even in the most turbulent environments, patterns can emerge and coherence can take root. As we continue our journey through these theories, we're reminded that the universe is a place of endless wonder, where even the smallest details can have profound implications. Next, we'll explore the anthropic principle, which suggests that the universe's quantum coherence might have been fine-tuned to allow for the emergence of life. The mysteries of the cosmos are far from solved, and each theory brings us closer to understanding the grand tapestry of existence. Stay with us, there's still so much to uncover. Now, let's turn our attention to a theory that shifts the focus from the chaotic beginnings of the universe to the delicate balance that makes life possible, the anthropic principle. This idea suggests that the universe's quantum coherence wasn't just a random occurrence, but might have been fine-tuned in a way that allowed life to emerge. It's a concept that raises profound questions about whether the universe was designed with purpose or if it's all a matter of chance. To understand the anthropic principle, we need to consider the remarkable precision of the laws of physics. For life to exist, certain conditions had to align perfectly. For example, the strength of gravity, the charge of an electron, and the rate of the universe's expansion all had to fall within incredibly narrow ranges. If any of these values were even slightly different, stars, planets, and life as we know it might never have formed. The anthropic principle argues that the universe's quantum coherence played a crucial role in setting these conditions, creating a stable environment where life could flourish. But how does quantum coherence fit into this picture? Think of it as the universe's way of maintaining order on a fundamental level. In the early moments of the cosmos, quantum coherence could have acted as a kind of tuning mechanism, ensuring that particles and forces interacted in just the right way to lay the groundwork for complexity. Without this coherence, the universe might have remained a chaotic soup of particles, never giving rise to the structures necessary for life. This leads us to a fascinating question. Was this fine-tuning intentional, or is it simply a result of chance? Some scientists argue that the anthropic principle points to a multiverse, a vast collection of universes, each with its own set of physical laws. In this scenario, our universe is just one of countless others, and it's no surprise that we find ourselves in the one where conditions are right for life. Others suggest that the fine-tuning of quantum coherence might hint at something deeper, perhaps even a form of cosmic design. The anthropic principle doesn't provide definitive answers, but it invites us to ponder the nature of existence itself. Why does the universe seem so perfectly suited for life? Is it a coincidence, or is there a deeper reason behind it? These questions challenge us to think beyond the physical laws and consider the philosophical implications of our existence. As we explore these ideas, we're reminded that the universe is not just a collection of particles and forces. It's a place where life can arise and thrive. The anthropic principle offers a unique perspective on the role of quantum coherence, suggesting that it might be more than just a scientific curiosity. It could be the key to understanding why we're here at all. With this in mind, let's move forward to our next theory, which takes us into the realm of neutrinos, particles so elusive yet so essential to the story of the universe's first quantum coherence. The journey continues, and the mysteries only grow deeper. Stay with us as we uncover more about the forces that shaped our cosmos. Now, let's venture into the shadowy world of neutrinos, particles so elusive that they barely interact with matter, yet they might hold the key to understanding the universe's first quantum coherence. These nearly massless particles, often called ghost particles, are among the most mysterious inhabitants of the cosmos. Despite their faint presence, neutrinos could have played a pivotal role in shaping the early universe, acting as silent architects of quantum order. To grasp their significance, we need to understand just how unique neutrinos are. Unlike other particles, neutrinos rarely interact with anything. They can pass through entire planets without a single collision. This ghostly behavior makes them incredibly difficult to detect, but it also means they were among the first particles to roam freely in the early universe, unhindered by the dense, chaotic environment that existed just after the Big Bang. Their ability to move through space without interference might have allowed them to influence the formation of quantum coherence on a cosmic scale. But how exactly could neutrinos have contributed to this process? One possibility lies in their sheer abundance. In the early universe, neutrinos were produced in staggering numbers, outnumbering even protons and electrons. This vast population of particles moving freely and interacting weakly could have created a subtle but widespread influence on the quantum state of the universe. Imagine a vast, invisible network of neutrinos subtly nudging particles into alignment, helping to establish the delicate balance needed for coherence to emerge. Another intriguing idea is that neutrinos might have acted as carriers of quantum information. In the early universe, where particles were densely packed and constantly interacting, neutrinos could have served as messengers, transmitting quantum states across vast distances. This transmission of information could have been crucial in synchronizing the behavior of particles, allowing coherence to spread and stabilize throughout the cosmos. In this way, neutrinos might have been the unsung heroes of the universe's first moments, quietly ensuring that order emerged from chaos. the role of neutrinos in quantum coherence also ties into their unique properties. Unlike other particles, neutrinos oscillate, meaning they can change their type as they travel through space. This oscillation could have introduced a dynamic element to the early universe, adding complexity to the quantum landscape. By constantly shifting their identity, neutrinos might have created a kind of quantum ripple effect, influencing the behavior of other particles and helping to establish the conditions necessary for coherence. Of course, much about neutrinos remains a mystery. Their exact mass, for instance, is still unknown, and their interactions are so weak that detecting them requires incredibly sensitive equipment. Yet, their potential role in the universe's first quantum coherence is a tantalizing possibility. If neutrinos did indeed play a part in this process, it would mean that even the most elusive particles had a hand in shaping the cosmos we see today. As we ponder the role of neutrinos, we're reminded that the universe's story is written not just by the obvious players, stars, galaxies, and black holes, but also by the subtle, almost invisible forces that operate behind the scenes. Neutrinos, with their ghostly presence, might have been one of these hidden architects, quietly guiding the universe toward coherence and complexity. With this in mind, let's turn our attention to the next theory, which explores how quantum gravity might have acted as a bridge between the quantum and classical worlds, enabling the first coherent structures to form. The journey through the mysteries of the early universe continues, and each step brings us closer to understanding the forces that shaped everything we know. Stay with us as we uncover more about the quantum foundations of our cosmos. Now, let's shift our focus to a theory that bridges the gap between the quantum and classical realms: quantum gravity. This concept suggests that quantum gravity might have played a crucial role in enabling the first coherent structures to form in the early universe. But what exactly is quantum gravity, and how could it have acted as this cosmic bridge? Quantum gravity is the theoretical framework that attempts to reconcile two of the most successful yet seemingly incompatible theories in physics: quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the force of gravity on cosmic scales. In the early universe, these two worlds, quantum and classical, were deeply intertwined, and quantum gravity could have been the key to harmonizing them. One of the central ideas here is that quantum gravity might have provided the mechanism for transitioning from the chaotic, probabilistic nature of the quantum world to the more orderly, deterministic behavior of the classical universe. In the moments following the Big Bang, the universe was a seething cauldron of quantum fluctuations, where particles popped in and out of existence and spacetime itself was highly unstable. Quantum gravity could have acted as a stabilizing force, smoothing out these fluctuations and allowing coherent structures to emerge. Imagine quantum gravity as a kind of cosmic mediator, negotiating between the wild, unpredictable quantum realm and the structured, predictable classical universe. This mediation might have involved the creation of spacetime itself, as quantum gravity theories suggest that spacetime could have emerged from a more fundamental quantum fabric. In this view, the first coherent structures, whether they were particles, fields, or even spacetime itself, were the result of quantum gravity's balancing act. Another fascinating aspect of this theory is the idea that quantum gravity could have facilitated the transfer of information between the quantum and classical worlds. In the early universe, where particles were densely packed and constantly interacting, quantum gravity might have ensured that information about quantum states was preserved and translated into classical behavior. This transfer of information could have been essential for establishing coherence, allowing the universe to transition from a state of quantum chaos to one of classical order. The role of quantum gravity also ties into the concept of spacetime curvature. In the early universe, the intense energy and density would have caused spacetime to curve dramatically. Quantum gravity could have moderated this curvature, preventing it from becoming too extreme and ensuring that the universe remained stable enough for coherence to take hold. This delicate balance between curvature and stability might have been the key to the universe's first coherent structures. Of course, quantum gravity remains one of the most challenging areas of theoretical physics, and much about it is still unknown. However, its potential role in the universe's first quantum coherence is a compelling idea. If quantum gravity did indeed act as a bridge between the quantum and classical worlds, it would mean that the very fabric of reality played a part in shaping the cosmos we see today. As we explore this theory, we're reminded that the universe's story is one of connections between particles, forces, and even the very laws of physics. Quantum gravity, with its ability to bridge worlds, might have been one of the most important connections of all, quietly guiding the universe toward coherence and complexity. With this in mind, let's turn our attention to the next theory, which delves into the role of cosmic strings, hypothetical one-dimensional defects in spacetime, and how they might have influenced the formation of quantum coherence. The journey through the mysteries of the early universe continues, and each step brings us closer to understanding the forces that shaped everything we know. Stay with us as we uncover more about the quantum foundations of our cosmos. Now, let's venture into a theory that takes us into the realm of the truly exotic cosmic strings. These hypothetical one-dimensional defects in spacetime are thought to have formed during the early universe, and they might have played a surprising role in shaping the first quantum coherence. But what exactly are cosmic strings, and how could they have influenced the universe's earliest moments? Cosmic strings are like cracks or wrinkles in the fabric of spacetime, remnants of a phase transition that occurred shortly after the Big Bang. Imagine the universe cooling down rapidly, much like water freezing into ice. Just as ice forms cracks as it solidifies, the universe might have developed these cosmic strings as it transitioned from a hot, dense state to a cooler, more stable one. These strings are incredibly thin but possess immense energy, stretching across vast distances and potentially influencing the structure of the cosmos. One of the key ways cosmic strings could have impacted quantum coherence is through their gravitational effects. Despite being incredibly thin, cosmic strings would have exerted a significant gravitational pull on their surroundings. This gravitational influence could have created localized regions of order within the otherwise chaotic early universe. Picture a cosmic string as a thread weaving through the fabric of spacetime, pulling particles and energy into alignment around it. These aligned regions might have served as the seeds for quantum coherence, providing a stable framework for coherent structures to emerge. Another intriguing possibility is that cosmic strings could have acted as conduits for energy and information. In the early universe, where particles were densely packed and constantly interacting, cosmic strings might have channeled energy in specific directions, creating pathways for coherence to spread. This could have allowed quantum coherence to propagate more efficiently, enabling the universe to transition from a state of disorder to one of order. Cosmic strings also have a unique property: they can oscillate and vibrate. These vibrations could have generated gravitational waves, ripples in spacetime that carry energy and information. In the early universe, these gravitational waves might have played a role in distributing energy and stabilizing quantum states, further contributing to the formation of coherence. Think of it as a cosmic symphony, with cosmic strings as the instruments creating vibrations that harmonize the universe. But cosmic strings aren't just passive players in this story. Some theories suggest that they could have actively interacted with quantum fields, influencing the behavior of particles and fields in their vicinity. This interaction might have created conditions where quantum coherence could flourish, acting as a kind of cosmic catalyst for order. In this way, cosmic strings could have been both architects and builders, shaping the universe's first coherent structures. Of course, cosmic strings remain hypothetical, and their existence has yet to be confirmed. However, their potential role in the early universe is a fascinating area of study. If they did exist, cosmic strings might have been one of the key players in the universe's journey from chaos to coherence, weaving the fabric of reality into the ordered cosmos we see today. As we explore this theory, we're reminded of the intricate and interconnected nature of the universe. Cosmic strings, with their ability to influence spacetime and quantum fields, might have been instrumental in shaping the cosmos. Their story is one of mystery and possibility, offering a glimpse into the forces that shaped the universe's earliest moments. With this in mind, let's turn our attention to the next theory, which examines the quantum measurement problem and its potential connection to the universe's first coherence. The journey through the mysteries of the early universe continues, and each step brings us closer to understanding the forces that shaped everything we know. Stay with us as we uncover more about the quantum foundations of our cosmos. Now, let's shift our focus to a theory that dives into one of the most puzzling questions in quantum physics, the quantum measurement problem. This mystery lies at the heart of understanding how quantum states transition from a realm of probabilities to definite outcomes, and it might hold the key to unraveling the universe's first quantum coherence. At its core, the quantum measurement problem asks a simple yet profound question. How does a quantum system, which exists in a superposition of multiple states, suddenly collapse into a single, observable state when measured? In the early universe, this question becomes even more intriguing. If quantum coherence was the foundation of the cosmos, how did the universe transition from a state of infinite possibilities to the structured reality we observe today? One possibility is that the quantum measurement problem isn't just a quirk of modern physics, but a fundamental process that shaped the early universe. Imagine the universe in its infancy, a seething sea of quantum fluctuations where every particle existed in a superposition of states. In this chaotic environment, the act of measurement, or something akin to it, might have played a crucial role in stabilizing these fluctuations, allowing coherent structures to emerge. Some theories suggest that the universe itself could have acted as a kind of measuring device. In this view, the interactions between particles and fields in the early cosmos might have triggered a natural collapse of quantum states, creating localized regions of coherence. Think of it as the universe observing itself, with each interaction nudging the system toward a more ordered state. Another angle explores the role of decoherence, a process where a quantum system loses its superposition due to interactions with its environment. In the early universe, the dense and energetic conditions might have caused rapid decoherence, forcing quantum states to collapse into definite outcomes. This process could have been the driving force behind the formation of the first coherent structures, setting the stage for the universe's evolution. But the quantum measurement problem also raises deeper questions about the nature of reality. If quantum states only become definite when observed, what does that mean for the universe's earliest moments? Some interpretations propose that consciousness itself might have played a role, suggesting that the act of observation, whether by an external entity or the universe itself, was essential for coherence to emerge. While this idea remains speculative, it highlights the profound connection between quantum mechanics and the origins of the cosmos. As we explore this theory, we're reminded of the delicate balance between order and chaos in the quantum realm. The quantum measurement problem challenges our understanding of reality, offering a glimpse into the mechanisms that might have shaped the universe's first moments of coherence. It's a reminder that even the smallest details of quantum physics can have cosmic consequences. With this in mind, let's turn our attention to the next theory, which examines the role of inflationary fields in the formation of quantum coherence. The journey through the mysteries of the early universe continues, and each step brings us closer to understanding the forces that shaped everything we know. Stay with us as we uncover more about the quantum foundations of our cosmos. Now, let's venture into a theory that takes us back to the very fabric of the early universe, the role of inflationary fields. These fields are thought to be the driving force behind the universe's rapid expansion, a phenomenon known as cosmic inflation. But beyond stretching the cosmos, inflationary fields might have also played a pivotal role in creating the conditions necessary for quantum coherence to emerge. Picture the universe in its earliest moments, a hot, dense, and chaotic environment where particles and energy were in constant flux. During this time, inflationary fields are believed to have caused the universe to expand exponentially, smoothing out irregularities and setting the stage for the large-scale structure we see today. But here's where it gets fascinating. This rapid expansion might have also influenced the quantum realm, creating the perfect conditions for coherence to take hold. One way to think about this is through the lens of energy. Inflationary fields carried immense energy, and as the universe expanded, this energy was distributed across vast distances. This distribution could have acted like a cosmic reset button, cooling the universe and allowing quantum systems to stabilize. In this calmer environment, particles could interact more predictably, paving the way for coherent structures to form. Another intriguing possibility is that inflationary fields themselves might have been quantum in nature. If these fields were subject to quantum fluctuations, they could have seeded tiny variations in the early universe. These fluctuations, stretched by inflation, might have served as the building blocks for quantum coherence. Imagine these fluctuations as ripples on a pond, growing larger and more defined as the universe expanded, eventually giving rise to coherent patterns on a cosmic scale. But how exactly did inflationary fields facilitate coherence? One idea is that the rapid expansion created a kind of quantum pressure, forcing particles into more stable, ordered states. This pressure could have acted like a cosmic sculptor, shaping the quantum foam of the early universe into coherent structures. Over time, these structures would have grown and evolved, laying the groundwork for the galaxies, stars, and planets we see today. It's also worth considering the interplay between inflationary fields and other quantum phenomena. For instance, the energy carried by these fields might have interacted with particles in ways that enhanced their coherence. This interaction could have been a key factor in transitioning the universe from a state of quantum chaos to one of order and structure. As we explore this theory, we're reminded of the intricate dance between expansion and coherence in the early universe. Inflationary fields didn't just stretch the cosmos, they might have also woven the threads of quantum coherence into the fabric of reality. It's a testament to the profound interconnectedness of the universe's earliest moments, where even the most rapid expansion could have had a hand in creating the order we observe today. With this in mind, let's turn our attention to the next theory, which examines the quantum to classical transition and how the universe shifted from a quantum state to the classical reality we know. The journey through the mysteries of the early universe continues, and each step brings us closer to understanding the forces that shaped everything we know. Stay with us as we uncover more about the quantum foundations of our cosmos. Now, let's shift our focus to a pivotal moment in the universe's history, the quantum to classical transition. This theory explores how the cosmos evolved from a state governed by the strange rules of quantum mechanics to the familiar, predictable world of classical physics we experience today. At the heart of this transition lies the concept of coherence, which played a crucial role in shaping the universe as we know it. In the early universe, everything was governed by quantum mechanics, where particles existed in superpositions, probabilities, and entangled states. But as the universe expanded and cooled, something remarkable happened. It began to transition from this quantum realm to a classical one. This shift wasn't instantaneous, it was a gradual process, influenced by the interplay of energy, particles, and the environment itself. One key idea is that decoherence played a central role in this transition. Decoherence occurs when quantum systems interact with their surroundings, causing their delicate quantum states to collapse into more definite classical ones. Imagine a quantum particle in a superposition existing in multiple states at once. As it interacts with other particles or fields, these interactions measure the particle, forcing it to settle into a single state. Over time, this process would have spread across the entire universe, transforming it from a quantum soup into a classical reality. But coherence wasn't just lost in this process, it was also a driving force. In the early universe, coherence allowed particles to interact in predictable ways, creating the conditions for structure to form. As the universe expanded, these coherent interactions became the foundation for the formation of atoms, molecules, and eventually galaxies. Without coherence, the universe might have remained a chaotic, formless expanse. Another fascinating aspect of this transition is the role of time. In the quantum realm, time is more fluid and less defined, but as the universe transitioned to a classical state, time became a more linear, measurable dimension. This shift allowed for the emergence of cause and effect, enabling the universe to evolve in a way that we can now study and understand. Some theories suggest that the quantum to classical transition wasn't uniform across the universe. Instead, it might have occurred in patches, with some regions transitioning earlier than others. This uneven process could explain why we see variations in the cosmic microwave background, the faint afterglow of the Big Bang, and why certain structures in the universe appear more ordered than others. As we reflect on this theory, we're reminded of the delicate balance between chaos and order in the early universe. The quantum to classical transition wasn't just a change in the rules of physics, it was a transformation that laid the groundwork for everything we see today. From the tiniest particles to the largest galaxies, this transition shaped the cosmos in ways we're still striving to understand. With this in mind, let's turn our attention to the next theory, which explores the role of supersymmetry in the universe's first quantum coherence. The journey through the mysteries of the early universe continues, and each step brings us closer to unraveling the forces that shaped reality itself. Stay with us as we dive deeper into the quantum foundations of our cosmos. Now, let's venture into the intriguing world of supersymmetry, a concept that could hold the key to understanding the universe's first quantum coherence. Supersymmetry, often abbreviated as SUSY, is a theoretical framework that proposes a profound symmetry between two fundamental classes of particles, fermions and bosons. Fermions, like electrons and quarks, are the building blocks of matter, while bosons, such as photons and gluons, are the carriers of forces. Supersymmetry suggests that every fermion has a bosonic partner, and every boson has a fermionic counterpart. This elegant symmetry could have played a pivotal role in the early universe, shaping the conditions for quantum coherence to emerge. In the chaotic environment of the early cosmos, supersymmetry might have provided a stabilizing influence. By linking particles across different categories, it could have created a harmonious balance, allowing quantum states to interact in predictable and coherent ways. Imagine a cosmic dance where every particle has a perfect partner, ensuring that energy and information flow smoothly across the universe. This symmetry could have been the foundation for the first coherent structures, setting the stage for the formation of atoms, stars, and galaxies. One of the most compelling aspects of supersymmetry is its potential to resolve some of the deepest mysteries in physics. For instance, it offers a possible explanation for the nature of dark matter, the invisible substance that makes up a significant portion of the universe's mass. If supersymmetry is correct, the lightest supersymmetric particle could be a candidate for dark matter, providing a bridge between the quantum and cosmic scales. This connection suggests that supersymmetry didn't just influence the early universe, it might still be shaping the cosmos today. However, supersymmetry remains a theoretical idea, as no supersymmetric particles have been detected so far. Despite this, its mathematical elegance and explanatory power make it a leading candidate for understanding the universe's fundamental structure. If supersymmetry did play a role in the first quantum coherence, it would mean that the universe's earliest moments were governed by a symmetry so profound that it continues to echo through the fabric of reality. As we explore this theory, we're reminded of the delicate interplay between symmetry and chaos in the cosmos. Supersymmetry offers a glimpse into a universe where every particle has a partner, and every interaction is part of a grand, unified design. While the search for supersymmetric particles continues, the idea itself inspires us to think about the universe in new and profound ways. With this in mind, let's turn our attention to the next theory, which delves into the controversial concept of the quantum Boltzmann brane. This idea challenges our understanding of reality itself, suggesting that the universe's coherence might be the result of a self-aware entity arising from random fluctuations. The mysteries of the early universe continue to unfold, and each theory brings us closer to understanding the forces that shaped our reality. Stay with us as we journey deeper into the quantum foundations of the cosmos. Now, let's step into one of the most mind-bending theories in modern physics, the quantum Boltzmann brane hypothesis. This idea challenges not just our understanding of the universe's first quantum coherence, but the very nature of reality itself. At its core, the Boltzmann brane hypothesis suggests that self-aware entities could spontaneously arise from random quantum fluctuations. These hypothetical entities, known as Boltzmann branes, might exist for only a fleeting moment, yet they could perceive a coherent universe around them. But how does this connect to the origins of quantum coherence in the cosmos? To understand this, we need to revisit the concept of entropy, a measure of disorder in the universe. According to the second law of thermodynamics, entropy tends to increase over time, leading to a more disordered state. However, in an infinite universe, random fluctuations can occasionally create pockets of order. In rare cases, these fluctuations might produce something as complex as a self-aware brane, complete with memories and perceptions of a coherent universe. This is the essence of the Boltzmann brane idea, a universe where coherence isn't a fundamental property, but rather a fleeting illusion created by chance. Now, let's take this a step further. If Boltzmann branes can arise from random fluctuations, could the universe's first quantum coherence have been the result of such an event? Imagine a scenario where a Boltzmann brane, or something akin to it, emerged in the early universe. Its brief existence might have created a localized region of coherence, influencing the surrounding quantum states and setting off a chain reaction that led to the universe's first coherent structures. This would mean that the coherence we observe today isn't a product of fundamental laws, but rather a cosmic accident, a random fluctuation that happened to shape the fabric of reality. Of course, this idea is highly controversial. Critics argue that the probability of a Boltzmann brane forming is astronomically low, making it an unlikely explanation for the universe's coherence. Others point out that if Boltzmann branes were common, we should expect to encounter more evidence of their existence. Yet, the hypothesis remains a fascinating thought experiment, pushing the boundaries of our understanding of quantum mechanics, cosmology, and the nature of consciousness itself. What makes the Boltzmann brane hypothesis so compelling is its ability to challenge our assumptions about reality. If coherence can arise from randomness, what does that say about the universe's fundamental nature? Are we, too, the product of a random fluctuation, perceiving a coherent world that might not exist as we think it does? These questions blur the line between physics and philosophy, inviting us to rethink our place in the cosmos. As we ponder this theory, it's worth noting that the Boltzmann brane hypothesis isn't just a wild speculation. It's a reminder of how little we truly understand about the universe's origins. It forces us to confront the limits of our knowledge and consider possibilities that might seem far-fetched, yet are grounded in the principles of quantum mechanics and thermodynamics. Whether or not Boltzmann branes played a role in the universe's first coherence, the idea itself opens up new avenues for exploration and discovery. With this in mind, let's turn our attention to the next theory, which explores the role of actions, hypothetical particles that might have contributed to early quantum coherence. As we continue our journey through the mysteries of the cosmos, each theory offers a unique perspective, deepening our understanding of the forces that shaped the universe. Stay with us as we unravel more of these fascinating ideas. Now, shifting our focus to another intriguing piece of the cosmic puzzle, let's explore the role of actions in the universe's first quantum coherence. Actions are hypothetical particles that were first proposed to solve a perplexing issue in physics known as the strong CP problem. This problem revolves around the question of why certain interactions between particles don't seem to follow the expected symmetry rules. Actions were introduced as a potential solution, but their implications go far beyond this initial purpose, extending into the realm of quantum coherence in the early universe. To understand how actions might have contributed to coherence, we need to look at their unique properties. Unlike other particles, actions are incredibly light and interact very weakly with matter, making them nearly invisible to detection. Yet, despite their elusive nature, they could have played a significant role in the early cosmos. One possibility is that actions, as they moved through the dense, high-energy environment of the early universe, created subtle ripples in the quantum fields around them. These ripples could have acted as seeds for coherence, helping to organize the chaotic quantum states into more structured patterns. Another fascinating aspect of actions is their connection to dark matter. Many scientists believe that actions could be a key component of dark matter, the mysterious substance that makes up a significant portion of the universe's mass. If actions are indeed part of dark matter, their presence in the early universe might have influenced the formation of quantum coherence on a large scale. Imagine actions as invisible architects subtly shaping the quantum landscape and laying the groundwork for the coherent structures we observe today. But how exactly could actions have achieved this? One theory suggests that actions, due to their unique properties, could have formed a kind of quantum network in the early universe. This network would have allowed information to be shared across vast distances, creating a web of coherence that connected different regions of space. In this scenario, actions wouldn't just be passive bystanders, they would be active participants in the universe's transition from chaos to order. Of course, like many ideas in theoretical physics, the role of actions in early quantum coherence remains speculative. Detecting actions is an enormous challenge, and their existence has yet to be confirmed. However, the search for these particles is ongoing, with experiments around the world designed to uncover their secrets. If actions are discovered, it could revolutionize our understanding of the universe's earliest moments and shed light on the origins of quantum coherence. As we consider the potential impact of actions, it's worth reflecting on how much we still have to learn about the cosmos. Each theory, from the Boltzmann brane hypothesis to the role of actions, offers a unique lens through which to view the universe's mysteries. Together, they paint a picture of a cosmos that is far more complex and interconnected than we might have imagined. With this in mind, let's turn our attention to the next theory, which delves into the concept of quantum Darwinism and its implications for the universe's first coherence. As we continue to explore these ideas, we'll uncover even more layers of the cosmic story, each one bringing us closer to understanding the forces that shaped our reality. Stay with us as we journey deeper into the quantum mysteries of the universe. Now, let's venture into the fascinating realm of quantum Darwinism, a theory that offers a fresh perspective on how the universe's first quantum coherence might have emerged. Quantum Darwinism proposes that certain quantum states are selected over others to become classical, effectively bridging the gap between the quantum and classical worlds. This idea challenges our traditional understanding of how quantum systems transition into the observable, classical reality we experience every day. At its core, quantum Darwinism suggests that not all quantum states are created equal. Instead, some states are more fit to survive and propagate, much like how natural selection operates in biology. These selected states are the ones that can be observed and measured repeatedly without collapsing into randomness. In other words, they become the stable, classical structures we see in the universe. This process of selection could have played a crucial role in establishing the first quantum coherence, creating a foundation for order in the early cosmos. To better understand this, imagine the early universe as a vast, chaotic sea of quantum possibilities. Within this sea, certain states, those that are more robust and less prone to disruption, begin to stand out. These states are copied or broadcast across the environment, making them more likely to be observed and measured. Over time, these repeated observations reinforce the coherence of these states, allowing them to dominate and shape the emerging classical reality. In this way, quantum Darwinism provides a mechanism for how the universe could have transitioned from a purely quantum state to the structured, classical world we know today. One of the most intriguing implications of quantum Darwinism is its connection to the concept of information. According to this hypothesis, the selected quantum states carry information that is shared and replicated across the environment. This sharing of information could have been a key factor in establishing coherence on a cosmic scale. Think of it as a cosmic game of telephone, where the most stable and reliable messages are the ones that get passed along, eventually shaping the universe's structure. But how does this relate to the universe's first quantum coherence? If quantum Darwinism is correct, then the early universe would have been a battleground of competing quantum states, with only the most stable and coherent ones surviving to shape reality. This process would have created a kind of quantum ecosystem, where coherence emerges as a natural outcome of selection and replication. It's a compelling idea that ties together the microscopic world of quantum mechanics with the macroscopic structure of the cosmos. Of course, like many theories in this field, quantum Darwinism is still a work in progress. While it offers a promising framework for understanding the transition from quantum to classical, many questions remain. For instance, what determines which quantum states are selected? And how does this process unfold in the extreme conditions of the early universe? These are questions that scientists are actively exploring, and the answers could reshape our understanding of reality itself. As we reflect on the implications of quantum Darwinism, it's clear that this theory adds another layer of depth to our exploration of the universe's first quantum coherence. It reminds us that the cosmos is not just a collection of random events, but a dynamic system where order emerges through selection and adaptation. With this in mind, let's turn our attention to the next theory, which explores the role of the Higgs field in the early universe. Stay with us as we continue to unravel the quantum mysteries that shaped our reality. Now, shifting our focus to another cornerstone of modern physics, let's explore the role of the Higgs field in the universe's first quantum coherence. The Higgs field is often referred to as the cosmic glue that gives particles their mass, but its influence may extend far beyond this fundamental role. In the early universe, this field could have played a pivotal part in shaping the conditions necessary for quantum coherence to emerge. To understand this, let's start with the basics. The Higgs field permeates all of space, interacting with particles to give them mass. Without it, particles would zip around at the speed of light, unable to form the stable structures we see today. But in the moments following the Big Bang, the Higgs field was in a state of flux, undergoing a dramatic transition known as symmetry breaking. This event marked the point when the field settled into its current state, giving rise to the masses of particles and setting the stage for the universe as we know it. Now, here's where things get fascinating. During this transition, the Higgs field could have created regions of stability in the otherwise chaotic early universe. These stable regions might have acted as seeds for quantum coherence, providing a framework for order to emerge from the quantum soup. Imagine the Higgs field as a sculptor, shaping the raw material of the universe into coherent structures by giving particles the mass they need to interact and form complex systems. One intriguing possibility is that the Higgs field's influence extended to the quantum level, stabilizing certain quantum states and allowing them to persist long enough to contribute to the universe's first coherence. This stabilization could have been crucial in the transition from a purely quantum state to the classical reality we observe today. In essence, the Higgs field might have acted as a kind of quantum referee, ensuring that only the most stable and coherent states survived the turbulent early universe. But the story doesn't end there. The Higgs field's role in quantum coherence could also be tied to its interactions with other fundamental forces and particles. For example, its interplay with the electromagnetic force or the strong nuclear force might have created additional layers of stability, further enhancing the conditions for coherence. This interconnectedness suggests that the Higgs field didn't act alone but was part of a larger cosmic dance, where multiple forces and fields worked together to shape the universe's early structure. Of course, this is still a developing area of research, and many questions remain. How exactly did the Higgs field interact with quantum states in the early universe, and what role did its fluctuations play in the emergence of coherence? These are questions that physicists are actively exploring, using both theoretical models and experimental data from particle accelerators like the Large Hadron Collider. As we consider the Higgs field's potential role in quantum coherence, it's clear that this field is more than just a mass giver. It's a key player in the cosmic story. Its influence may have been subtle, but its impact on the universe's structure and coherence could have been profound. With this in mind, let's turn our attention to the next theory, which delves into the quantum many-worlds interpretation and its implications for the universe's first coherence. Stay with us as we continue to uncover the quantum mysteries that shaped our reality. Now, let's venture into one of the most mind-bending theories in quantum mechanics, the many-worlds interpretation. This idea suggests that every possible outcome of a quantum event actually happens, but in separate, branching realities. So, how does this relate to the universe's first quantum coherence? Let's break it down. In the early universe, quantum states were incredibly unstable, with countless possibilities existing simultaneously. According to the many-worlds interpretation, each of these possibilities didn't just vanish. They branched off into their own distinct realities. This means that the universe's first coherence might not have been a single, definitive event, but rather a process unfolding across an infinite number of parallel universes. Imagine the early universe as a tree with countless branches. Each branch represents a different outcome of quantum interactions, and each one contributes to the overall coherence of the cosmos. In some branches, coherence might have emerged quickly, while in others, it could have taken longer or even failed entirely. But in the grand scheme of things, the many-worlds interpretation suggests that coherence wasn't just a one-time event. It was a sprawling, interconnected phenomenon spanning countless realities. This idea also raises fascinating questions about the nature of reality itself. If every possible quantum outcome exists in its own universe, then the coherence we observe in our universe might just be one thread in a vast cosmic tapestry. It's a humbling thought, isn't it? The many-worlds interpretation challenges us to think beyond our single reality and consider the possibility that the universe's first coherence was part of a much larger, more complex process. But how does this branching of realities actually lead to coherence? One possibility is that the act of branching itself creates a kind of feedback loop, where stable quantum states are reinforced across multiple realities. In other words, the more a particular quantum state appears across different branches, the more likely it is to persist and contribute to the overall coherence of the universe. It's almost as if the many worlds interpretation provides a natural mechanism for selecting the most stable and coherent states. Of course, this theory is still highly speculative, and it's not without its critics. Some argue that the many worlds interpretation is untestable, while others question whether it truly explains the emergence of coherence. But even if it remains a theoretical framework, it offers a unique perspective on the universe's earliest moments, one that invites us to think bigger and bolder about the nature of reality. As we ponder the implications of the many worlds interpretation, it's worth remembering that this is just one piece of the puzzle. The universe's first quantum coherence likely involved a combination of factors, from the Higgs field to quantum entanglement and beyond. And with that in mind, let's turn our attention to the next theory, which explores the role of primordial gravitational waves in shaping the universe's early coherence. Stay tuned as we continue to unravel the quantum mysteries that define our existence. Now, let's shift our focus to another fascinating piece of the cosmic puzzle: primordial gravitational waves. These ripples in space-time, born from the violent energy of the Big Bang, might hold the key to understanding how the universe's first quantum coherence came to be. But what exactly are primordial gravitational waves, and how could they have influenced the early universe? Picture the Big Bang as a massive explosion, not just of matter and energy, but of space-time itself. In the chaotic aftermath, space-time would have been stretched and squeezed, creating ripples that traveled outward like waves on a cosmic ocean. These ripples, known as primordial gravitational waves, carry with them a snapshot of the universe's earliest moments. They're like echoes from the dawn of time, and they might have played a crucial role in shaping the universe's first quantum coherence. One idea is that these gravitational waves acted as a kind of cosmic messenger, carrying information about the quantum states that existed in the early universe. As they rippled through space-time, they could have influenced the way quantum particles interacted, helping to synchronize their behavior and create coherence on a grand scale. Think of it like a conductor guiding an orchestra. The gravitational waves might have provided the rhythm and structure needed for the universe's quantum symphony to emerge. But how do we know these waves even exist? While we haven't directly detected primordial gravitational waves yet, scientists have found indirect evidence through observations of the cosmic microwave background, the faint afterglow of the Big Bang. Tiny patterns in this ancient light could be the fingerprints of gravitational waves, offering clues about the universe's quantum origins. If we can one day detect these waves directly, it could open a window into the very first moments of the cosmos and shed light on how quantum coherence first took hold. Another intriguing possibility is that primordial gravitational waves didn't just carry information. They might have actively shaped the quantum landscape of the early universe. As these waves passed through space-time, they could have created regions of higher and lower energy, acting like a cosmic sculptor molding the quantum foam into coherent structures. This process might have been essential for stabilizing the universe's quantum states and setting the stage for the emergence of matter, energy, and even life itself. Of course, this theory is still in its early stages, and there's much we don't yet understand. But the idea that gravitational waves could have played a role in the universe's first quantum coherence is a tantalizing one. It connects the largest scales of the cosmos, the ripples in space-time, to the smallest scales of quantum mechanics, offering a glimpse into how the universe might have organized itself from chaos into order. As we explore this theory, it's worth reflecting on how interconnected the universe truly is. From the tiniest quantum particles to the vast ripples of space-time, everything seems to be part of a grand cosmic dance. And with that in mind, let's turn our attention to the next theory, which dives into the idea that the universe's coherence might be rooted in something even more fundamental: quantum information theory. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's take a step into a realm where the universe itself might be built not just on matter or energy, but on something even more fundamental: information. This brings us to the intriguing concept of quantum information theory, a framework that suggests the universe's first quantum coherence could be rooted in the very fabric of information itself. But what does it mean for information to be the building block of reality, and how could this idea explain the coherence of the early universe? At its core, quantum information theory proposes that everything in the universe, every particle, every force, every interaction, can be described in terms of information. Think of it like this: instead of seeing the universe as a collection of physical objects, imagine it as a vast, interconnected network of data. In this view, the quantum states of particles aren't just random fluctuations, they're bits of information like the ones and zeros in a computer. And just as a computer uses information to perform tasks, the universe might use quantum information to create structure, order, and coherence. One of the most fascinating aspects of this theory is the idea that quantum coherence could emerge from the way information is processed and shared. In the early universe, as particles interacted and exchanged information, these exchanges might have created a kind of cosmic harmony, synchronizing quantum states across vast distances. It's like a cosmic internet where every particle is a node and every interaction is a transfer of data. Over time, this flow of information could have led to the emergence of coherent structures, setting the stage for the universe we see today. But how does this connect to the Big Bang? Some scientists suggest that the universe's first moments were a kind of quantum computation, where the laws of physics acted like algorithms, processing information to create the conditions for coherence. In this scenario, the Big Bang wasn't just an explosion of matter and energy, it was the birth of a quantum information system where every particle carried a piece of the cosmic code. As the universe expanded and cooled, this information network grew more complex, eventually giving rise to the coherent structures we observe today. Of course, this raises a profound question: what is the source of this information? Some theories propose that the universe's information is encoded in its fundamental constants, like the speed of light or the charge of an electron. Others suggest that information might be a property of spacetime itself, woven into the fabric of reality. Whatever the answer, the idea that information underpins the universe's coherence is a powerful one, offering a new way to understand the cosmos. As we explore this theory, it's worth considering how it connects to other ideas we've discussed. From primordial gravitational waves to quantum entanglement, many of the universe's mysteries seem to revolve around the flow and organization of information. Could it be that the universe's first quantum coherence was the result of a cosmic information network, where every particle played a role in shaping reality? It's a thought-provoking possibility, and one that challenges us to rethink our understanding of the universe. With this in mind, let's turn our attention to the next theory, which takes us even further back in time, to the Planck epoch, the earliest moment in the universe's history. What role might quantum coherence have played in this unimaginably brief but crucial period? Stay with us as we continue to explore the mysteries of the cosmos. Now, let's journey back to the very beginning, a time so early in the universe's history that it defies our everyday understanding of reality. This brings us to the Planck epoch, a fleeting moment just after the Big Bang, where the universe was unimaginably small, hot, and dense. During this period, the laws of physics as we know them break down and quantum effects dominate. It's here, in this chaotic and mysterious era, that we might find the seeds of the universe's first quantum coherence. The Planck epoch is named after Max Planck, the physicist who introduced the concept of quantum mechanics. It's the earliest phase of the universe, lasting only about 10 to the power of -43 seconds. To put that into perspective, it's a timescale so short that it's almost impossible to comprehend. During this time, the universe was so compact that all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, all-encompassing force. This was a realm where quantum fluctuations ruled, and spacetime itself was a seething, turbulent sea of energy. But how could quantum coherence emerge in such a chaotic environment? Some theories suggest that even in this extreme state, certain patterns or symmetries might have begun to form. Imagine a stormy ocean where waves crash and churn unpredictably. Yet, beneath the chaos, there are underlying rhythms patterns that emerge from the interplay of forces. In the Planck epoch, these rhythms could have been the first hints of quantum coherence, as particles and energy began to synchronize in ways that would later shape the universe. One intriguing idea is that the Planck epoch acted as a kind of quantum forge, where the fundamental building blocks of reality were hammered into shape. As the universe expanded and cooled, these early quantum states might have stabilized, creating the first coherent structures. Think of it like a symphony tuning up before a performance. At first, the sounds are discordant and chaotic, but as the musicians find their rhythm, harmony begins to emerge. In the same way, the Planck epoch might have been the universe's tuning phase, setting the stage for the cosmic symphony that followed. Another possibility is that the Planck epoch was a time of quantum entanglement on a cosmic scale. In this scenario, particles and energy were so tightly interconnected that their quantum states were instantly correlated, no matter how far apart they were. This entanglement could have created a kind of universal coherence where the entire universe was, in a sense, in sync. As the universe expanded, this coherence might have been preserved, influencing the formation of galaxies, stars, and even life itself. Of course, the Planck epoch remains one of the most challenging areas of study in physics. Our current theories struggle to describe what happened during this time, and many questions remain unanswered. But the idea that quantum coherence might have emerged in this primordial era is a compelling one, offering a glimpse into how the universe transitioned from chaos to order. It's a reminder that even in the most extreme conditions, the seeds of structure and harmony can take root. As we reflect on the Planck epoch, it's fascinating to consider how this brief moment might have shaped everything that came after. From the formation of the first particles to the emergence of galaxies, the echoes of this early coherence could still be felt today. And with that, let's turn our attention to the next theory, which explores an even more controversial idea: the role of consciousness in the universe's first quantum coherence. Stay with us as we continue to unravel the mysteries of the cosmos. Now, shifting our focus to a theory that bridges the gap between the physical and the metaphysical, we arrive at the quantum consciousness hypothesis. This idea proposes that consciousness itself might have played a crucial role in the universe's first quantum coherence, intertwining the mysteries of the mind with the fundamental laws of physics. It's a concept that challenges our understanding of reality, suggesting that the observer, or perhaps consciousness itself, could be a key player in the cosmic dance of quantum mechanics. At its core, the quantum consciousness hypothesis suggests that the act of observation or awareness might influence quantum states, potentially stabilizing or even creating coherence. This idea draws from the famous double-slit experiment in quantum physics, where particles behave differently when observed. Some interpretations of this phenomenon imply that consciousness could be a fundamental aspect of the universe, shaping reality at its most basic level. If this is true, then consciousness might not just be a byproduct of the universe, but a foundational element that helped bring order to the chaos of the early cosmos. One way to think about this is to imagine the universe as a vast, interconnected network of quantum possibilities. In this view, consciousness acts like a filter, collapsing these possibilities into a coherent reality. During the Planck epoch, when the universe was in a state of extreme quantum fluctuation, the presence of some form of proto-consciousness could have guided the emergence of coherence. It's a bold idea, suggesting that the universe might have woken up to itself, creating order through a kind of cosmic self-awareness. Of course, this hypothesis is highly speculative and remains a topic of intense debate. Critics argue that attributing such a role to consciousness risks venturing into the realm of philosophy rather than science. Yet, proponents point to intriguing connections between quantum mechanics and the brain, such as the idea that quantum processes might underlie neural activity. If consciousness is indeed rooted in quantum phenomena, it's not unreasonable to consider that it could have played a role in the universe's earliest moments. What makes this theory particularly fascinating is its implications for our understanding of reality. If consciousness is fundamental, then the universe might be far more interconnected and alive than we ever imagined. It raises profound questions about the nature of existence, the relationship between mind and matter, and whether the universe itself could possess a form of awareness. While these ideas remain on the fringes of mainstream science, they invite us to think beyond the boundaries of traditional physics and explore the deeper mysteries of the cosmos. As we ponder the quantum consciousness hypothesis, it's worth considering how this idea might reshape our view of the universe. Could consciousness have been the spark that ignited the first quantum coherence, setting the stage for the emergence of galaxies, stars, and life? It's a question that challenges us to rethink not only the origins of the universe but also our place within it. And with that, let's turn our attention to the next theory, which explores another fascinating quantum phenomenon, the Casimir effect, and its potential role in the universe's first coherence. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's dive into another intriguing quantum phenomenon that could hold clues to the universe's first coherence, the Casimir effect. This effect, rooted in the strange behavior of vacuum energy, offers a fascinating perspective on how the early universe might have transitioned from chaos to order. At its heart, the Casimir effect reveals the hidden forces at play in the quantum realm, forces that could have shaped the very fabric of reality in those first moments. The Casimir effect occurs when two uncharged parallel plates are placed extremely close to each other in a vacuum. Despite the absence of any obvious force, the plates are drawn together. This happens because the vacuum isn't empty, it's teeming with virtual particles that constantly pop in and out of existence. These particles create fluctuations in the vacuum energy, and when the plates are close enough, the energy outside them becomes greater than the energy between them, resulting in a net force that pulls the plates together. It's a subtle yet profound demonstration of how quantum mechanics can produce tangible effects from seemingly nothing. So, how might this relate to the universe's first quantum coherence? During the Planck epoch, the universe was a seething sea of quantum fluctuations, with energy fields and particles interacting in ways we're still trying to understand. The Casimir effect suggests that even in this chaotic environment, certain regions could have experienced a kind of quantum tug, where fluctuations in vacuum energy created localized areas of stability. These pockets of order might have acted as seeds for the larger-scale coherence that eventually gave rise to the structured universe we see today. One way to think about this is to imagine the early universe as a turbulent ocean, with waves crashing in every direction. The Casimir effect could have been like a calm eddy, where the chaotic energy of the quantum foam settled into a more ordered state. Over time, these eddies could have grown, merging and amplifying until they formed the first coherent structures. It's a compelling idea, suggesting that the same quantum forces we observe in the lab today might have played a crucial role in shaping the cosmos billions of years ago. Of course, this theory is still speculative, and connecting the Casimir effect to the universe's first coherence requires bridging a vast gap in our understanding. However, it's an exciting avenue of exploration, offering a glimpse into how the strange and counterintuitive world of quantum mechanics might have influenced the birth of the universe. By studying phenomena like the Casimir effect, we're not just uncovering the secrets of the quantum realm, we're also piecing together the story of how everything came to be. As we reflect on the Casimir effect's potential role in the early universe, it's worth considering how such subtle quantum forces could have had such profound consequences. Could the same vacuum energy that pulls tiny plates together have also helped stitch the fabric of spacetime into a coherent whole? It's a question that invites us to explore the deeper connections between the quantum and the cosmic. And with that, let's turn our attention to the final theory in our journey, the quantum simulation hypothesis. Stay with us as we explore the idea that the universe itself might be a quantum simulation, and what that could mean for our understanding of reality. Now, let's venture into one of the most mind-bending ideas in modern physics, the quantum simulation hypothesis. This theory proposes that the universe we perceive might not be the fundamental reality, but rather a highly advanced quantum simulation. Imagine for a moment that everything around us, the stars, the planets, even our own thoughts, could be the product of an intricate computational program running on a quantum computer of unimaginable power. It's a concept that challenges our very understanding of existence and raises profound questions about the nature of reality itself. The idea of a simulated universe isn't entirely new. Philosophers have long pondered whether our experiences are real or mere illusions, but the quantum simulation hypothesis takes this a step further by grounding it in the principles of quantum mechanics. At its core, this theory suggests that the universe's coherence, the orderly behavior of particles and forces, could be the result of a quantum simulation. In this scenario, the laws of physics we observe might simply be the rules programmed into the simulation, and the quantum coherence we see could be the underlying code that keeps everything running smoothly. One of the key arguments supporting this hypothesis comes from the nature of quantum mechanics itself. Quantum systems are inherently probabilistic, meaning they don't follow the deterministic rules of classical physics. Instead, they operate in a way that resembles the behavior of computational algorithms, where outcomes are calculated based on probabilities. This has led some scientists to speculate that the universe might be running on a quantum computer, with each particle's behavior determined by a set of programmed instructions. If this is true, then the coherence we observe in the universe could be the result of a finely tuned simulation, designed to create a stable and consistent reality. But how could such a simulation work? One possibility is that the universe is divided into discrete units of spacetime, much like the pixels on a screen or the bits in a computer. These units would interact according to the rules of the simulation, creating the illusion of a continuous, flowing reality. This idea aligns with some interpretations of quantum gravity, which suggest that spacetime itself might be quantized at the smallest scales. If so, then the universe's coherence could be the result of these discrete units working together in harmony, much like the code in a computer program. Of course, the quantum simulation hypothesis is not without its challenges. For one, it raises the question of who or what could have created such a simulation. Are we the creations of an advanced civilization running experiments in a virtual universe, or could the simulation be self-sustaining, emerging from the fundamental laws of quantum mechanics? These questions push the boundaries of both science and philosophy, inviting us to reconsider what it means to exist. Despite its speculative nature, the quantum simulation hypothesis offers a fascinating perspective on the universe's first quantum coherence. If the cosmos is indeed a simulation, then the coherence we observe might not be a natural phenomenon but rather a carefully designed feature of the program. This idea forces us to confront the possibility that our reality is far stranger than we ever imagined, and that the answers to the universe's deepest mysteries might lie not in the stars but in the code that underpins them. As we wrap up our exploration of the quantum simulation hypothesis, it's worth reflecting on the implications of this idea. Could the universe's coherence be the result of a quantum simulation? And if so, what does that mean for our understanding of reality? These questions remind us that the universe is full of mysteries waiting to be uncovered, and that the journey to understand them is as thrilling as the answers themselves. With that, we conclude our journey through 30 theories about the universe's first quantum coherence, but the exploration of the cosmos is far from over. What do you think about these ideas? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the universe. As we bring our journey through these 30 theories to a close, it's remarkable to reflect on the sheer diversity of ideas surrounding the universe's first quantum coherence. From the explosive beginnings of the Big Bang to the speculative realms of quantum simulations, each theory offers a unique lens through which we can explore the origins of order in the cosmos. Whether it's the holographic principle painting the universe as a two-dimensional code, or the role of dark energy shaping its expansion, these ideas remind us that the universe is far more intricate and mysterious than we often realize. What's truly fascinating is how these theories, though vastly different, all point to one central truth. The universe's coherence is not just a random occurrence but a fundamental feature that has shaped everything we see and experience. Whether it emerged from quantum entanglement, the collision of branes, or even the possibility of a simulated reality, each theory challenges us to think beyond the familiar and embrace the unknown. As we stand on the edge of these cosmic mysteries, one question lingers: what does it all mean for us? Are we simply observers in a vast, unfolding quantum dance, or is there something more profound at play? The beauty of these theories lies not just in their answers, but in the questions they inspire. They invite us to keep exploring, keep questioning, and keep marveling at the wonders of the universe. So, what do you think? Which of these theories resonates with you the most? Do you believe the universe's coherence is a natural phenomenon, or could it be the result of something even more extraordinary? Share your thoughts in the comments below. I'd love to hear your perspective. And if you enjoyed this deep dive into the mysteries of the cosmos, don't forget to like, subscribe, and hit the notification bell for more explorations into the universe's greatest enigmas. The cosmos is vast, and the journey to understand it is just beginning.